Before I go in details, I would like to acknowledge our wonderful team. This is experts in density functional theory, tight binding, molecular dynamics, quantum computation, TKI modeling, machine learning, as well as experimental validation. This is the outline of my talk. Luckily, because of all the fantastic talks we heard in the last day or this day as well, I think I can quickly go over some material design principle, basics, superconductors, brief introduction to AI, superconductor database that we developed and how we applied AI models to it, how we can also use GPT model for accelerating experiments, and finally some words about reproducibility and benchmarking. So let's get started with the first topic, which is material design. So before this, a brief, I don't need to introduce to you what are superconductors, but I believe these are one of the most fascinating and class of materials in condensed matter physics. In the last 100 years or so, there have been several Nobel Prizes in this field, and there have been several types of superconductors, type 1, type 2, conventional, unconventional, high pressure BCA superconductors, and here are some examples. Our goal for this talk will be primarily on conventional superconductors. So let's talk about material design. So the basic principle of material design is processing structure property performance, PSPP mantra or guideline. So as a forward task, you go for example, structure to property, but for inverse model, you go from property to structure. So it's just, I personally see as Google versus ChatGPT. So suppose you want to find good restaurants near me. So you'll go to a Google, find all the list of restaurants, and then search which has the best rating and so on, and then select. That's like screening based way of funnel like approach. While if you go to ChatGPT, find me a restaurant near this area, and boom, there are the candidates. I mean, kind of something like this, right? So it's kind of the very direct and very popular approach nowadays for material design, inverse approach of material design. So it's also allow us to go beyond funnel like or screening based approaches. Now, when I say especially structure property, structure might mean atomic structure, microstructure, grain structure, segment structure. Property may be scalar properties like band gap, transition temperature, hardness. It can be multi-value or spectral properties, X-ray diffraction, ellipsometry, or it can be image like microscopy images and so on. So our idea is to go from forward as well as inverse. Now, the idea is very fascinating, but this is very challenging task because, and we heard about this both experimentally and computationally, there is a huge combinatorial challenge, and especially for inverse model, to my knowledge, there are absolutely no physics-based model for inverse material design. So we have to rely on something like AI models. Now, there are some models for inverse design, such as genetic algorithm, Monte Carlo, cluster expansion, Bayesian optimization, but they are very limited on their ability to handle complex material spaces. Also, anytime you have AI mirror models, 50% of your problem is finding good diverse data sets. And then that's the second component, diverse database. And of course, you have a good strategy to know whether it's working or not. Benchmarking is very important. Now, when I say AI model, there are different type of AI model. These can be descriptor-based, graph-based, and text-based, and there are different type of models. So you have to select which one to choose from. Now, the inverse design idea is not new. I saw one of the first paper from ALIGNN in 2018 in Nature Chemistry. And from there, we have expanded on inverse design of superconductors with collaboration with Microsoft, AtomGPT model, and DiffRact-GPT model, which we'll talk about. And as I said, there are a lot of researchers who are working on this field, and we already heard some of the talks in the field, and several exciting works coming on every day or every week in this field. So this was a brief introduction to material design and superconductors. Now we have to talk briefly about AI methods. So now, if you are not super familiar with deep learning or machine learning in general, I will strongly recommend you this article we wrote called Recent Advances in Applications of Deep Learning Methods in Material Science. And it talks about 5 domains of applications of machine learning for materials. It can be chemical formula, it can be atomic structure, text, spectra or pattern, and images. 5 domains, and for 5 domains it gives you details. We also have collaborated and contributed to a book called AI for Science, a deep learning revolution, which is more than just material science, and a few other review articles. Now, I want to point out computers do not know physics, chemistry, mathematics, all this information. What they know is numbers. So how we can transmit our sophisticated information to computer. This is a very challenging task, and there are many methods and models developed for this. These are the 3 models that our group have developed. So the first is called classical force field inspired descriptor. So we heard about MACPI kind of descriptor. So we have a atomic structure. You can take, for example, average atomic number, boiling point, and so on, but it doesn't contain chemistry information. So the idea is, at least in 2018, we tried to include total radial distribution function, angle distribution function, and the hydral distribution function in, and that gives you 1557 descriptor for each material, and that can give you high accurate models. In 2021, 3 years from the CFIT descriptor, we developed this ALIGNN framework, which we also heard from the previous talk, to have line graph to improve accuracy, especially for electronic properties. And last year or so, we proposed this GPT model. So here, instead of representing materially as a fingerprint or as a graph, we represent as a text, and then it can be used for both forward, that is structure to property, or property to structure kind of model. And both all these models are available on the US NIST repository. And I would like to emphasize, we put a lot of effort in making these repositories are well to use, well documented, a lot of examples. They're not breaking, so a lot of software parts goes into maintaining these infrastructures. We talk about the CFIT descriptors, so I'll not spend too much time, but just the idea was to improve structural fingerprinting as well as chemical fingerprinting in descriptor-based model. So graph neural network model, we already heard from Patrick very nicely. I don't need to give details about this, but I would like to point out, when we started this work with graph neural network in 2018, we saw that most of the graph neural network do not contain angle information. So we started to use at least 4 or 5 different methods to include angles, and we found this line graph approach was most efficient. So as we also heard from the previous talk, if you have a node, this blue sphere and red spheres, you can distinguish these based on the node features such as electronegativity, atomic number, and if you have edges as bonds, you can think of if you have a material with 10 atoms, one with 1,000 atoms, so how can we uniformly kind of represent this? So you can have a kind of a basis function, or AKA in a simple form, histogram of bonds, and that in a radial basis function approach, and that will give you the atomicity graph. But now you can consider another graph where edges are the nodes and the edge pairs are the new nodes, new edges, and that will give you a line graph. And this way you can capture angles, and we can have similar representation for angle, maybe radial basis function, spherical, or Legendre polynomial, any other type of basis function is fine. So we found that, especially in 2021, this was published, and we found especially important for property prediction like electronic properties, and we can predict for graph level like global energy, atomic charges, forces on atom, Lennard-Jones parameter, tight binding parameter, and so on, using this graph framework. So in 2021, we published this ALIGNN framework, and it beat all the, at least that time, existing model. And 2 years from then, we published this ALIGNN FF, Unified Graph Neural Network Force Field for the periodic table. And basically, we took the Jarvis DFT data set, which has around 80,000 materials, and we developed a unified machine learning force field that can be used to run MD simulation or run geometry optimization for any combination of 89 elements from the periodic table with certain approximations. Now, next is, you can see that both descriptor-based model and ALIGNN graph-based models are very good for forward models. For inverse model, they can be very challenging. So one of the alternate approach we have is GPT model. So at this point, I think most of us are familiar with ChatGPT model. They are really fascinating, and I think most of us use it a lot of times. There's a fun research. There's about 65% of the code that is generated nowadays is all from ChatGPT. So it's definitely an impactful research. But if you look for a materials design problem, first of all, you'll see this it's not really trained on a lot of materials data. So a lot of materials data is not even there yet because the periodic table combination and so on. And second is the models of the ChatGPT are proprietary. So you don't know what the model is trained on. And third, and most importantly, the ChatGPT outputs are non-reproducible. So you ask a question today and you ask the question 3 minutes from today or tomorrow, it will be a different response, which is not good for science. So the idea of AtomGPT was to have a model which can be customized for material design, and it can be trained on the scientific knowledge, and it will be open access and reproducible. That was the motivation behind the AtomGPT model. And this model, as I said, can be used for both forward and inverse design. So again, computers, you can explain atomic structure in terms of formula, space group, bond length, and so on, like tetrahedral and so on, other orientation, using a software package we developed called ChemNLP. And you can describe this and then predict properties like transition temperature. Now, inverse method is where you say here is a format called alpaca. So here we describe my superconductor material. This is my formula. This is a superconducting transition temperature we want. This is DFT based, of course. And then I want to generate the lattice length and angle and coordinate and atom types, and it will generate you this kind of structure with length, angles, and the element types and their coordinates. And this both text to text mapping. That's why transformer. And I think some of the speaker also mentioned we also tried different combination of representing this structure, but having length and angle in this format works really well when we generate this kind of outputs. And once you have the atomic structure generator, you can use machine learning force field like ALIGNN and use a pre-trained model like ALIGNN, and then that will be candidate of DFT, and then DFT will guide you to experiments. So it's kind of three-step process. I'd like to briefly talk about this GPT architecture. So this is based on a paper called Attention is All You Need. And I think this is one of the most highest papers in the history of mankind, which about 200,000 citations in 8 years. And there's a lot of details, but let me try to make it super simple. So suppose you ask a question, hi, how are you? And the response is, I am fine. Now, again, computers do not know hi, how are you? They understand numbers. So what you can do is consider a dictionary, which has about 200,000 words or similar, and you can find where hi occurs, comma occurs, how occurs, r occurs, u occurs, and you give a token index. And similarly, you have a token index for your outputs. Now you can consider entire internet, Wikipedia, New York Times, whatever, and this process called tokenization. You can tokenize it and establish a relationship between the input token and the output token in a fancy way, kind of to find out which tokens are important. That is called attention. And there's a basic idea. I mean, of course, there are a lot of maths involved, but that's the basic idea of GPT models. Now, there are thousands of GPT models. For AtomGPT, we use this model called Mistral AI 7 billion parameter model. And we have tried several models like Llama, Gemma, Quen, and so on. For some reason, this Mistral model seems to be very promising for materials design in whatever we have tested. And after we generated this model for superconductor, this AtomGPT model is now available in Hugging Face, and I heard a lot of companies and so on are using this for their own applications, which is nice to hear. So these were our AI models. Now I'll talk about critical component database generation, without which a whole AI model is pointless, right? So having good data sets. So we'll be using a database called Jarvis, which is available at jarvis.dis.gov. The idea is to combine density functional theory, classical force field, machine learning, and experiments to design or optimize the materials. And there are several review articles about this. So you can feel free to check it out. So now I would like to point out this is not just a database like density functional theory, or it also have classical force field, tight binding, dynamical mean field theory, quantum Monte Carlo, and so on. But we also have tools like ALIGNN, AtomGPT, atomistic quantum computation, machine vision for computers, CHIPS FF for benchmarking classical force field or machine learning force field, Intermat for interface design, tight binding model, TV3Pi, and so on. I'll be primarily focused on AtomGPT and ALIGNN. We also have interactive web apps. The databases are like static images. Web apps are kind of lets you work with a new data. So this web app benchmarking is a critical thing at NIST. So we have a Jarvis leaderboard, which you also heard in the previous talk. So you have at least five domains: AI, electronic structure, quantum, experiment, forceful. We also emphasize on tutorials. So we have several Google Colab notebooks, hundreds of notebooks, outreach events. So we organize quantum matters and AI workshops. So one of the AI workshops is happening in July. Feel free to register. So some of the success story of this database and infrastructure, we started in 2017. So we are one of the youngest, I believe, infrastructure out there for materials. But very interestingly, we have about 200,000 users worldwide, 4,000 citations, 50 articles. We focus on less number of materials and more on quality of the data and more number of properties. And we have several million of downloads of our data set and of code. Just one of this database is Jarvis DFT. So we have about 80,000 materials, and we go beyond PBE level databases. So yesterday I was listening to some talk how having OCT88 and this kind of van der Waal functional are important for functional materials. So we use van der Waal functional for all non-van der Waal and van der Waal banded material. We have a meta GZA called TBMBJ, which gives very good band gaps. We also have spin orbit coupling data. We converge K point and cutoff for each material. Energy force convergence are very strictly enforced. We have elastic tensor data, piezoelectric data, dielectric data, electric field gradient for NMR, superconducting transition temperature, Raman spectra, solar cell efficiency, and so on. So primarily focusing on the superconductor data set. This is the outlook of the Jarvis DFT. So you might be familiar with this kind of structure where you go and click on the elements and see details of each material. Now we have taken this to a next level. We have developed this infrastructure called ChatGPT Material Explorer. So you can go to ChatGPT and talk about Jarvis. So suppose you want to look for aluminum oxide. So it will not just give you the data from Jarvis, but it will also tell you what does it mean. And this is especially important for newcomers and people who are not expert in this field. And you can chat about it all day. And the idea is in 10 years, if we can have a model or infrastructure where we can chat about, I want a superconductor with this critical field or this transition temperature. First, do the calculation, synthesize, characterize, ship me home. If we can do that in 10 years, I think that will be the real AI age. I think we are not still in the AI age. So that is the motivation behind this ChatGPT Material Explorer, and not just database search, but it also comes with integrated ALIGNN model, and we are going to add GPT model, our diffract GPT, AtomGPT model in Material Explorer as well. So let's talk about one of the database, 3D BCS superconductor dataset. So we heard how Supercon dataset from the Japan has mainly chemical structure, chemical formula, not atomic structure. So we developed the first full atomic structure high throughput database. So for this, we use the BCS theory. So in BCS theory, you have divide temperature and density of states at the Fermi level at least. So we took the Jarvis DFT dataset. At that time, we have 55,000 materials. And we had elastic tensor data, so we can calculate divide temperature. And from there, we search for high divide temperature, high DOS material. And then we developed a workflow using quantum espresso to calculate a Macmillan-Allen-Dyne formula-based transition temperature. And based on phonon stability and thermodynamical stability, we computationally discovered 112 new materials. And this was published in the Nature Design Computational Materials, Designing High TC Superconductors. And this was the key advancement, I think, in the superconductor atomic structure field. And after this paper, I believe a lot of research in Germany and others have expanded this idea for many other larger data sets. We spend a lot of time in benchmarking and parameter sensitivity of this mu star and very other K point, Q point convergence, and comparison with experiments. And the candidates that we propose is part of this 2022 NPJ paper. This database is also available at Jarvis, called jarvis.gov/supercon. So you can go there and search for example, magnesium boride, and it will give you the details about that material and so on. So once you have the database, you can do machine learning training. So we have the ALIGNN model and CFIT model. So we start predicting for these 1,000 data points, the TC, the omega log, and the lambda coupling parameters. We found that it's much easier to predict omega log than lambda, and deep learning model seems to be better, but TC prediction is still very challenging. And we also predict the divide temperature and density of states at the Fermi level. We also found that instead of directly predicting transition temperature, we can predict the Eliashberg function. And we found that it can give you up to 6% improvement if you predict first Eliashberg function and then TC instead of directly predicting TC. And using this model, we apply this model on 431,000 material in crystallographic open data set and found 8,293 candidate superconductors using this machine learning model. We extended this ambient pressure superconductor to high pressure superconductor. So we took the Jarvis DFT, find all the material with hydrogen, low hull, low gap, and so on, and apply pressure in quantum espresso. And if they are BCS based, of course, they will have high temperature, and we propose new candidates, hydride materials at high pressure. We extend this for not just 3D but also 2D materials. So we have Jarvis 2D material database, and we took materials from Jarvis 2D and with low magnetic moment, low gap, and with Macmillan and Dine formulation and dynamical stable, we proposed some new 2D materials. Now this is fine. This is still funnel kind of approach, graph based or DFT based forward design. How about inverse design? So we collaborate with Microsoft. They have this model called crystal diffusion variational autoencoder. And the idea is once you have a graph, you have something called embedding feature or hidden feature. From this hidden feature, you can predict a property, or you can write three models which will predict lattice parameters, a number of atoms, and the composition, and gradually have a noising and denoising to give you the full atomic structure. So we use this model to generate 3,000 new superconductor candidate, and then use Macmillan-Allen formula based discovery of dynamically stable superconductors. But when we are working with this, we found that there are several challenges. First of all, this model is extremely difficult to train, and it generates a lot of asymmetric structures like P1 structure kind of thing, so which is not very good for superconductor design. There's still a lot of symmetric structure, but a lot of them are non-symmetric, so which is challenging. So that was the motivation of GPT models. So this AtomGPT model, we tried for both forward and inverse design. And especially we tried at least four properties like formation energy, GGA band gap, meta GGA band gap, and superconducting transition temperature. And we found that this GPT models are good for electronic properties like band gap and TC, but not so good for energy quantity like formation energy. So graph neural network models are still very good for that kind of classical quantities. Not for forward model, but also for inverse model. We compare on carbon 24 and our superconductor data set that we developed, and it was better and faster and than CDVA model, at least for the RMSE metric. I believe there are a lot of metrics for inverse material design. I think the real success of inverse material design is actually validating with DFT or so on, instead of focusing too much on this matrix. And so we'll talk about that. So one of the candidates is NB2B generated from GPT model. So again, this is just a proof of concept. So please take it with a grain of salt. This proof of concept that we generated at superconductors with AtomGPT and verified with DFT that it was actual superconductor. Now I'll talk about accelerated experiments quickly. So after spending 4 years of PhD at University of Florida, actually, with DFT MD, and about 8-9 years working at NIST for DFT database and machine learning, last year I started learning some experiments. So I'm learning diffraction, X-ray diffraction, which is really fascinating. And as a computational person, when you learn experiment, it opens completely new horizon. It's just beautiful. So I'm learning X-ray diffraction, TEM, EBSD, and so on. So here's an example for diffract GPT. When I was learning performing X-ray diffraction experiment, especially for powders, I found that there are a lot of matching kind of methods, and there's no physics-based model for given X-ray diffraction pattern predicting the crystal structure. And this is because there's a reduction of chemical and three-dimensional structure information into 1D pattern. So we developed this diffract GPT model, which will be used to generate crystal structure from diffraction pattern. And this was recently published in Journal of Physical Chemistry Letters and was highlighted as the cover of the journal. So suppose you have X-ray diffraction pattern, and then you can have background subtraction. You can do at least two ways. First, the normal way is you can take X-ray diffraction pattern, match with ICDD or Jarvis or any other database, and then give structural candidates. We actually have a web app for this, jarvis.nist.gov/jxrd, and you can do that search. But more fun part is you can have the X-ray diffraction pattern, suppose from 0 to 90 degree 2 theta, and suppose you take a bin of 0.3 degree 2 theta, and then for each bin you count how many peaks are there, and then you round it off to 2 digits, and then you concatenate it in Python using a string variable like a comma or new line character, and that becomes a string. That is my X or input, and my output is the CIF file or similar to CIF file. So here's a prompt where chemical formula is this, XRD is this, generated with lattice matrix. That's the idea. Now this is called tokenization. You can, once you have this pattern, you can tokenize it, and then you have three scenarios. Number one, you know the chemistry. Number two, you don't know fully the chemistry, but you know some element list comparison. And number three, you know exact formula. So you have three type of suggestions from the diffract GPT model, and then you can further optimize with ALIGNN, unified graph neural force field to get the candidates. So of course, for this training, we need data set. So we could have used ICDD, but we used the Jarvis DFT data set to generate X-ray diffraction pattern and powder X-ray diffraction pattern, and we compare with experiment that I did. So these are for some superconductor like magnesium boride and so on. So you can see that they compare very well. So you have good confidence on our simulated diffraction pattern. So once you have the simulated diffraction pattern, we developed model for diffract GPT with no formula, with element list, and with formula. And this is the RMC error. And we found that the diffract GPT with formula was the least error. We also compare with gradient boosting and convolutional neural network. Of course, they don't give you the full atomic structure, but lattice parameters. But diffract GPT formula will not only give you the lattice parameter, but also full crystal structure. So here's an example. So you give an input spectra, you will give it to the model, it will generate a crystal structure, and then from the crystal structure, you can use the powder diffraction pattern routine to get the diffraction pattern, and then you can further refine that structure to get the atomic structure. So we tried this for many models, not just for perfect materials, we also tried for defect materials. So although we trained this model only on perfect data set, we saw that even if we have an atom, two atom system, and you displace one of the atom, basically your point group remains the same. You see that your X-ray intensity ups and goes up and down, right? So we found that even though we did not train the model, it can generate those structure. Of course, there are several limitations, but it's a good proof of concept. We are extending this diffraction idea for magnetization measurement at NIST. So we are measuring the transition temperature of several candidates that we proposed using PPMS. And the idea would be to have similar GPT model for magnetization. And final part, I don't know how much time you have, but finally, quickly, I'll talk about the Jarvis leaderboard, which we heard about. So this is based, motivated from this paper called 1500 Scientists Lift the Lid on Reproducibility. This paper is published in Nature and highly cited. So in this paper, they show that only 0.5% to 30% papers out there are reproducible. More than 70% papers are non-reproducible, which is insane. So how can we have an infrastructure to enhance reproducibility, have transparency, ability to have benchmarking, and so on. So that was the idea of Jarvis leaderboard. And you can see this is the website we have. It has several categories like AI, atomic structure, force field, quantum computation, experiments, and so on. And it's not just theory, but also experiment. So we were funded from the CHIPS project. We got a $5.1 million award to work on computational metrology, and this is one of the products from this metrology work. So I'll just quickly, there are 300 benchmarks in this Jarvis leaderboard. I'll just quickly show you one of them or a few of them. So there's a forward design of predicting TC model with GPT model, CFIT model, CGCN model. There's similarly for inverse material design, GPT model, CDVA model. Now you have a new model, you can add it here, and then it will be enhance the visibility of your work, also reproducibility. Not just theory, but we also have experimental benchmark. So we are trying to conduct round robin experiments. Suppose you have powder superconductors, we can collaborate with Oak Ridge National Lab, Navy, and other national lab, so that we can have uncertainty in predicting TC or high or magnetic field for experimental samples. So it may not be it doesn't have to be thousands of materials, but also few materials as a good example for how reproducible both theory and experiments will be. So with that, these are some of the key papers I have on database, inverse design with diffusion model, 2D materials, high pressure hydride, GPT model, and the diffract GPT models. And again, if you have any question and have ideas to collaborate, I'm more than happy to talk to you. Please feel free to reach out at kamal.chaudhary@nist.gov. You can also connect me on LinkedIn, X, Tweet, and YouTube. I also have a YouTube channel. So you can watch some of my videos anytime I have a new paper or something. I usually have a paper update in my YouTube channel. So with that, I'd like to thank you again for listening to this talk and inviting me again here, and happy to answer any question if you have.